So Chapter 8 continues with our connection between a population and a simple random sample of that population and what inferences you can make about that population. And we focus mostly on when we knew about the parameters of the population and what it looks like in the sampling distribution. But Chapter 8, more frequently, we're not going to have the information about the population. We're inferring that information from a sample. So instead of just looking at one number, like we looked at, which we will call a point estimate, we're going to start looking at an interval of plausible values and how confident we are, which is called the confidence level. So this is all going to be connected to the normal curve, which is why I wanted you to look at that as a reminder of all the things you knew about it. We're also going to, as always, see how sample size affects the quality of our inference as well as the confidence level, how that affects the length of the interval. And then we'll also look at other kinds of bias and how that affects a confidence interval. Mostly if it's a bad sample, you can't make a confidence interval, but that's just the simple version of it. Remember in Chapter 7 we were making inferences. We were not making inferences about the population. We were just actually figuring out how populations and sampling distributions are connected to one another. We did find out, for example, that p hat and x bar, their means they're considered unbiased estimators because the means of their distribution is equal to the mean of the population. So, and we also knew that sampling had lots of variability due to chance only, but we can lessen variability when we increase the sample size. For Chapter 7, the focus was on how the sampling distribution related to the population parameters when these parameters are known. But really, we barely know those things. And so we're going to talk now about how the population can be inferred about using an unbiased sample. So last chapter we called a statement about the sample that we were hoping would be a good estimator of a population parameter. This chapter focuses on those point estimates as a starting point, and then we're going to create an interval of plausible values. So the point estimator is the thing that allows us to find that point, that gives us a good estimate of the population parameter, and the point estimate is the statistic itself. It's the number itself. We found out last chapter, for example, range, bad, bias doesn't work, whereas very commonly used unbiased estimators are mean. The sample mean x bar is equal to the proportion parameter of mu, and the mean of p hat distribution is equal to the proportion p in the population. So we know about some unbiased point estimators that give us a good point estimate, which gives us kind of a middle. Estimating parameters needs to acknowledge that repeated sampling can yield different results, and we need to look at that and start looking at a larger way of looking at it, which is an interval. Once again, last chapter gave us all the information we knew about the population and showed how sampling distributions are related to it, but most of the time we don't have all that information about the population, and we're using the sampling to understand information about the population. We're going to look at a made-up situation where we don't know the population mu, but we do know the standard deviation, just so we can get a sense of what's going on here. So let's imagine we've taken lots and lots and lots and lots and lots of simple random samples of n equals 16. And after we're all done and we've taken the mean of those means, we get 240.79 is the average mean of the means. And then we know that the population was 20, since we're using 16 as our n, then the standard deviation is going to be 5. So in repeated samples, we saw in Chapter 7 that the values of x bar will create a normal distribution, and we know that the mean in this particular case, I'm telling you that the mean is, because we've looked at all these things, is 240.79, and the standard deviation was the standard deviation divided by n squared. So we know that 2 standard deviations away would be 10 from x bar, and we know that it would be 10 back from x bar as well. So here we'd have 2 standard deviations above and below, which is 95% of the data, which means 95%, that interval 10 below, and 10 above will capture the true mu in about 95% of all the sample sizes. So we look at that interval from 230.79 to 250.79, and we say that we have 95% confidence that the interval from 230.79 to 250.79 will capture the true mean of the population. The big idea of a confidence interval is where instead of looking at a single point that we're going to infer is the true value of the population parameter. We're looking at the fact that the sampling distribution of x bar tells us how close to the true mean, mu, the sample mean x bar is likely to be. And instead of a single point, we're going to be looking at an interval. And that interval is going to tell us not only what the center point is, but it's going to give us a margin of error above and below that center point. That tells us a couple of things. It gives us the interval of plausible values for that parameter of interest. It's the interval that the true value will be captured by, and that the difference between the point estimate and the true parameter will be less than the margin of error in C% of the samples. In our case, right here, we're talking about C% being 95%. And so that margin of error is based on that 2 standard deviations away, above and below. And then the confidence level gives a success rate of the method for calculating that interval. So once again, the C% is related to z-scores, between which that percent of sample values would lie. So your confidence interval is the values in between which your true population mean or population proportion is going to be captured. And the confidence level, on the other hand, has to do with the overall capture rate, the percent of, if we were sampling over and over and over again, what percent of those times we would truly capture it. And that's based on a z-score. And this margin of error component comes from z-scores, and we'll get to that in a moment. But right here we have a bunch of different SRSs of 16, and the intervals based on each of those capture the true value except this one. So 95% of the time the intervals captured the unknown population mean, in this case, is what we're looking for. So in our sample, the estimate was 240.79. And our margin error was 2 standard deviations above and 2 standard deviations away. So it's plus 10 and minus 10. So this is how you write it in this form. And then we can, of course, write it in interval form, which is 230.79 all the way to 250.79. And this template right here, we're going to use over and over and over again when we're asked to interpret a confidence interval. You've got to pay attention to both the interval itself, the estimate and the margin of error, as well as the C% confidence. In this case, we're looking at 95% confidence level. So we would say that we're 95% confident from the interval from 230.79 to 250.79 includes the true value of mu, of the population mean. And we're going to want to use these templates. I'm going to show you the second one as well in the next slide. So once again, get your interval idea straight versus your levels. Your intervals is the lowest point to the highest point that we expect the unknown parameter to be in, and this is the template you're going to use. We are C% confident that the interval from blah 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 to blah 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 captures the actual value of, normally it's going to be either the population mean or the population proportion. And then the level has to do with the percent that we are confidence going to fall under there. So a real common one is 95. So it's going to be 2 standard deviations above and 2 standard deviations below. But basically the idea for the confidence level, if we take many samples of the same size of the population, about 95% of them will result in an interval that captures the actual parameter value. So the confidence level tells us how likely it is that the method we are using will produce an interval that captures the population parameter if we use it many times. The confidence interval gives us a set of plausible values for that parameter, and we interpret confidence levels and confidence intervals in much the same way, whether we're estimating a population mean, proportion, or some other parameter, but mostly we're focusing on the mean and the proportion. By the way, the confidence level does not, and this is a common error, does not tell us the chance that a particular confidence interval captures the population parameter, but that like 95% of the intervals that are created will capture it. When we construct confidence intervals, the confidence level, that C%, comes from the normal curve and how many standard deviations away from it is from the curve. So 95% confidence is based on 2 standard deviations away. 99.7% confident that we would have the intervals would capture the true parameter of interest. That would be a much wider, it would be all the way to 3 standard deviations away from the mean. But the interval would be wider. And if you wanted your interval to be smaller, then your confidence level is going to be a smaller percentage, right? Like if we went only between 1 and -1 standard deviations, we'd only be 68% confident that the intervals that were produced over many repetitions would include the parameter of interest. So you kind of got to balance it. But in general, this allows us to understand the formula for finding confidence intervals, which we're going to start with our statistic of interest, whether it's the X bar or the P hat. Critical value is how far away from the mean are we interested in getting, how big of an interval are we interested, what percentage of confidence do we want, and that critical value is very often 2, because we do 2 standard deviations away, so it's 95% confident, but the critical value comes from the z-scores that relate to those demarcations of lower and upper boundaries. And then their standard deviation of the statistic might be the standard deviation of the X bar, or it might be the standard deviation of the P hat. So that's why we learned those formulas last time. But this is in general how it rolls. So the form is always that statistic plus or minus the critical value times the standard deviation of the statistic. And critical value just relates to the z-score. The margin of error is that critical value. You take the middle and you add that margin of error and you subtract that margin of error, and it's a critical value times the standard deviation of the statistic. By the way, we can decrease that margin of error by increasing n, because we know that increasing n shrinks the variability, or we can decrease the confidence level by choosing a different confidence level and therefore choosing a different critical value based on that confidence level. Once we choose that confidence level, I just said that. The critical value depends on the confidence level and the sampling distribution of the statistic, and the greater confidence requires a larger critical value. So if you really wanted 99.7%, you would have a critical value of 3. If you wanted 95, you'd have a critical value of 2. If you only wanted 68, you'd have a critical value of 1. And we're going to look at what if you wanted 90% or 80%. And then we're going to look at how you find the appropriate z-scores to use. And the standard deviation of the statistic depends on sample size n. Because of that, the higher the sample size, the smaller that margin of error is going to be anyway. Here are 2 important cautions to keep in mind when constructing and interpreting confidence intervals. Our method of calculation assumes that the data comes from an SRS of size n from the population of interest. That means it has to have a good sampling method. Can't be voluntary, can't be convenience. It's got to be a good, solid SRS. And the margin of error in a confidence interval covers only the chance due to random sampling and not any bias that comes from bad sampling. So from this, you should be able to find a point estimate and create that margin of error depending on the percent of confidence that you're interested in. You can interpret a confidence interval in the context of a problem, which we'll do more of that in class, and interpret a confidence level in context so you know how that relates to z-scores. And then you describe how the sample size and the confidence level affects the length of the confidence interval, which is generally increase the sample size, shrink the margin of error, increase the confidence level, you're growing that margin of error. And then, of course, bad sampling, don't use your confidence level. Don't use your confidence interval because you can't build one out of a bad sample.